All right, Gen Chem, today we are going to talk about Le Chatelier's principle. And this principle we use a lot when we're talking about systems that are in equilibrium. I just want to remind you a little bit about equilibrium. Equilibrium means that a system is no longer experiencing any net change, but things are still reacting. So equilibrium is where the rate of the forward reaction is equal to the rate of the reverse reaction. So we still have individual molecules changing. So let's get a pen here. So equilibrium is where the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so it appears as if nothing is changing, but individual molecules are still reacting and still making products and still going back to reactants. Okay, so this theory is about 130 years old. So in 1888, we have a French chemist named Henri Louis Le Chatelier. He discovered that there were ways to control and make reactions more productive. Isn't that what we always want? We want things to be more productive. Saves money in the long run, right? Making things more productive. He proposed what is now called Le Chatelier's principle. So if a stress is applied to a system at equilibrium, the system shifts in order to relieve that stress. A stress is any kind of a change in a system at equilibrium that would upset the equilibrium. So let's enumerate some of the stresses or some of the changes that we could do this. So stresses include the following. We can change, and I'm going to use delta for our symbol for change. We can change the temperature. We can change the concentration. We can change the pressure. And we can, we can change the concentration, we can change the temperature, we can change the pressure, we can change the size of the reaction barrel. So we can change the size of the reaction vessel, and that really changes the pressure. These are primarily the things that we can do. We can raise or lower the temperature, we can increase or decrease the concentration, we can increase or decrease the pressure, and we can increase or decrease the size of the reaction vessel, which also changes the pressure. Okay? Now, just like we think of for when we did our equilibrium constants, we only used things that were in the gas state or the aqueous state. Things that are in the liquid state or the solid state do not have bearing on this as long as there's at least some of it. Okay, so we only really pay attention to things that are in the gas state or in the aqueous or dissolved state. Okay, so the other thing that is really important with Le Chatelier is we're going to think of a reaction as kind of an old-fashioned balance. I don't know if you've ever played around with an old-fashioned balance, but they have like a couple of plates on them, and you have to have them balance in order to stay steady. If you've ever weighed stuff on a pan compared to an actual, like a scale that we use now. But we're going to pretend like we have an old-fashioned balance, okay? And we're going to weigh things on both sides. We're going to think of one side being the reactants, and one side being the products. And we want to keep it as even as possible. Each of these things will disrupt that evenness, that balance, the equilibrium. And then we've got to figure out which side do we need to make heavier again to get it to be back into equilibrium. Okay? So let's think about this. We've got our reactants here, and we've got our products here. And yes, heat or our energy will be thought of as a product in this reaction. If it's on the left-hand side, it will be thought of as a reactant. Okay? Remember, we can change temperature. That is something that will upset this equilibrium. Okay, so let's think about this really quickly. Let's get another color. So if I increase my nitrogen is on my reactant side. That is going to make my reactant side of my balance go down. I'm going to really increase my reactants. So how do I get it to be even again? Which side do I need to make heavier? I need to make my product side heavier. I need to make more products. So I am going to shift right because the products are on the right-hand side of the equation. So I'm going to shift right to make more products to make that balance correct. Same thing would happen if I increased my hydrogen. If I increased my hydrogen, I would make my reactant side of that balance really heavy. And I need to make my product side, this side, much more heavier to put it back into balance. So I would make more products, so I would shift right because the products are on the right side. Okay? If I decrease my ammonia, now decreasing, we're going to look at the ammonia right here. Decreasing is the same thing as taking it away. So if I have my ammonia on my product side and if I take it away, what does it do to that balance pan? It makes that balance pan really light. So that's going to go up here on my product side. And it's going to make my reactants heavier. So I need to make my product side heavier again to get it back into alignment. So once again, I would shift right. I would want to make more products. Okay, if I increase my temperature, so I'm increasing my temperature, I'm putting more of that in. Okay, wouldn't that make my product side really heavy? That would make my reactant side really light. I need to make my reactant side heavy again so it evens out. So I would actually shift left. I would shift left to make more reactants. So this would be shift left to make more reactants. Okay? If I increase the pressure, what we have to do is we have to look at how many moles of gas we have on both sides. So we're going to look at the coefficient. Actually, that one's too dark. Let's use green. So if I don't have a coefficient, it's listed as 1, right? So I have 1 nitrogen, 3 hydrogens. So that gives me a grand total of 4 moles of gas on my reactant side. On my product side, I have 2 moles of gas. So on my product side, I have 2 moles of gas. Okay, so if I'm increasing the pressure, that means I'm squeezing things together. If you're squeezed together, are you going to want to be as big as possible or as small as possible? You're going to want to be as small as possible. 2 is a lot smaller than 4. So we're going to shift right so we have a smaller volume that we can occupy. We're going to shift right. Whoops, wrong thing here. Shift right. Okay. Now, if I add a catalyst, it indeed does speed up the reaction, but it speeds up the reaction both ways. So if I add a catalyst, the rates just go faster, but they still are equal. So there's no shift with a catalyst. Okay? All right, let's look at this chart really quick here. So if I want to take this carbon monoxide and 3 hydrogens and make methane and water, notice these are all in the gas stage. If I want to shift to the right, I'm going to add a reactant that makes that reactant side really heavy, so I need to make more products. Or I can remove a product, which makes the product side really light, and I'm going to have to make more product to get that to shift left or shift right. Okay? If I shift left, I'm going to remove a reactant, which takes some of the reactants out, makes that reactant side over here really light. So I'm going to have to make more reactants and shift left to make that heavy again. Or I can add a product which makes the product side really heavy once again, and I have to shift to the left to make more reactants. So using this scale or this balance idea really helps me understand what's going on. Okay. Now, if we do the other way with energy, so if I have an exothermic reaction, this means that the delta H is on the right-hand side. I'm releasing energy. Notice heat is part of our products. It's on the right-hand side. If I raise the temperature, that makes the product side really heavy. So I need to shift left to make more reactants, right? If I add more here, I'm going to have to shift left to make more reactants to even that out again. But if I remove this heat, this makes this really light. So I'm going to have to shift right to make that even out again. Okay? Now, in an endothermic reaction, delta H, or the heat, is on the left. It's on the product side. Okay, notice it's on the product side here. Okay, if I want to shift to the right, I'm going to add heat. I'm going to raise the temperature because this makes the reactant side really heavy. So to even it out, I'm going to have to make more products to even that out. Okay, if I lower the temperature, it's the same as removing that heat. It's taking that heat away. So it makes that reactant side really light. So we're going to have to shift left to make more reactants to generate some more heat. Okay? So take a look at those. Make sure that those make sense for you for both adding and removing products or reactants and adding or removing heat or energy. Okay? Or raising or lowering the temperature is another way that we can phrase that. Okay. So here we go. Example 8. How would each of the following changes affect the equilibrium or the equilibrium position of the system used to produce methanol from carbon monoxide and hydrogen? Okay, so we've got carbon monoxide and hydrogen going to make methanol and heat. Notice heat is a product, so this is an exothermic reaction. Okay, I'm going to add carbon monoxide to the system. That is putting more weight on the reactant side, making that heavy. So to even it out, I need to make the same amount of weight on the product side, so I'm going to shift right. Okay, I'm going to shift right. Now, I want you to do the rest of these on your own and check back in a minute or two. Okay. You ready to check? All right, what if I cool the system? It's the same as removing this heat. That's going to make the product side really light. So I need to shift to the product side, shift right to make more heat. Okay, what if I add a catalyst? This makes the reaction faster, but it makes the reaction faster in both ways, right? There will be no shift. Catalysts just make things go faster. It doesn't shift the equilibrium. What if I remove methanol from the system? Take that away. That's going to make the product side really light. So in order to make the product side heavy again, I am going to need to shift right. What if I decrease the volume? Decreasing the volume is the same as increasing the pressure. I'm squeezing things together. So I'm going to look at the number of moles I have on both sides of this equation. So here we go. We've got 1 plus 2. So I've got 3 moles over here. And I've got 1 mole over here. So if I'm increasing the pressure, making that smush into smaller space, decreasing the volume, am I going to want to have a lot of moles or as little as possible? If I'm doing a smaller space, I'm going to have as little as possible. So this product side has the smaller amount of moles. It only has 1. So I'm going to shift right to make the smaller amount of moles. How'd you do on that? All right, here's some more examples. All right, ethylene reacts with hydrogen to form ethane. Okay, so I have ethylene plus hydrogen going to give me ethane and heat. Once again, this is an exothermic reaction. Heat is a product. How would I change the temperature? Would I raise it? Would I lower it of this equilibrium system in order to accomplish some of the following? Okay. What if I wanted to increase the amount of ethane? I want to increase this. So I want this to shift right. How would I do that? By just using the heat. Heat is a product, so if I want it to shift right, I'm going to remove the products. So if I remove the heat, that is the same as lowering the temperature. So I would lower the temperature here. Okay. What if I wanted to decrease the concentration of ethylene? So ethylene is right here, and I want to decrease that concentration. If I want to decrease that concentration, that means I want to make more products, right? I want to shift right. So I want to shift right that same way. And the way I can shift right is by removing that heat, right? I can remove that heat so to drive that right. So I'm going to lower the temperature. Okay, what if I want to increase the amount of hydrogen? So we're going to look at this. I want to take this and I want to increase this. So that means I actually want to shift left because I want to make more reactants. How do I shift this left with just the temperature? Can I increase the heat to make this drive to the left? I can. So I am going to increase the heat or raise the temperature. Okay, how are you doing on those? All right, we are going to do some more practice for this next video. We'll talk to you later, just in a minute.